Good morning to all. This is Dr. Padma, Assistant Professor, Department of Physics, Institute of Aeronautical Engineering. Today's topic is the basic Mosfet operation. So, topics are Introduction, Mosfet structure, current voltage relationship, concepts. Introduction. So, the current in a Mosfet is due to the flow of charge in the inversion layer. So, the current in the Mosfet is due to the flow of charge in the inversion layer or channel region which is adjacent to oxide to semiconductor interface. So the current in Mosfet which is due to the flow of charge in the inversion layer or the channel region which is adjacent to the oxide and semiconductor interface. So the current in the Mosfet is due to the flow of charges which is adjacent to the oxide and semiconductor interface. So we will discuss about the creation of the inversion layer charge in the enhancement P-type mass capacitors. So the creation of the inversion layer charge in the enhancement type mass capacitors we already discussed. So we may also have depletion type devices in which a channel is already existed the zero voltages. So in depletion devices, the channel is already existed the zero voltage or zero gate voltage. So in MOSFETs, the current is due to the flow of charge carriers in the inversion layer or the channel region which is adjacent to the oxide and semiconductor interface. So in depletion type devices, the channel is already existed the zero voltage or zero bias voltage. So there are four basic MOSFET devices are there. So figure 1 shows the N-channel enhancement mode MOSFET. So we will discuss about the enhancement type or enhancement mode MOSFETs. So this is the circuit cross section and circuit. This is the circuit symbol, cross section and circuit symbol for the N-channel enhancement mode MOSFET. So this is the substrate. Substrate is known as the body. Source, yes, gate and drain. This is the N plus region, this is the P type. So this is the cross section and circuit symbol of the N-channel enhancement mode MOSFET. So in the enhancement mode notation, the idea is that the semiconductor substrate is not inverted directly under the oxide with zero voltage. So here the substrate is not inverted directly. So the idea behind the enhancement mode MOSFET is the semiconductor substrate is not inverted directly under the oxide with zero gate voltage. So in enhancement mode, so the semiconductor substrate is not inverted directly under the oxide layer with the zero gate voltage. So a positive gate voltage induces an electron inversion layer which then connects the N-type source and the N-type drain regions. So here we are giving the positive gate voltage which induces the electron inversion layer. So which induces the electron inversion layer which then connects to the N-type source and N-type drain regions. So the source terminal is the source of carriers. So the carriers are coming from the source. So the source terminal is the source of carriers that flow through the channel to the drain. So the charge carriers are coming from the source and flow through the channel. So the source terminal is the source of carriers. So the carriers are flowing through the channel to the drain. So the source of carriers are coming from the source. Those are flow through the channel and reaches the drain terminals. So the carriers are coming from the source. Those are flowing through the channel and reaches to the drain terminal. So for this N-channel device, electrons flow from the source to the drain. So the conventional current will enter the drain and leave the source. So if you take the N-channel device, So in n-channel device, charge carriers means electrons. So electrons are flow from the source to the drain. So the conventional current will enter the drain and leave the source. So the conventional circuit symbol for this n-channel enhancement mode device in the previous figure. So if you take the n-channel device, the electrons are flow from the source to the drain. So the conventional current will enter the drain and which leaves the source. So the conventional circuit symbol is already shown in the figure. So figure 2 shows the n-channel depletion mode. So in the previous case, we shown that that is the enhancement mode. Now figure 2 shows the n-channel depletion mode. So n-channel region exists under the oxide with 0 voltage applied to the gate or 0 gate voltage. 0 gate voltage. So this is the cross section and circuit symbol for the n-channel depletion mode. Here this is the substrate. So here the gate is the n-channel, drain D, gate G, source S. So the cross section and circuit symbol for an n-channel depletion mode of the MOSFET. Here we are using the p-type substrate, that is the body is the p-type substrate. So this is the n-channel depletion mode, cross sectional diagram of the n-channel depletion mode. So however, we have shown that the threshold voltage of the MOS device with a p-type substrate may be negative. So for a p-type substrate, the threshold voltage is negative. So the threshold voltage of a MOS device with a p-type substrate, we are using the p-type substrate, that may be negative. This means that the electron inversion layer already exists with the 0 gate voltage applied. Here the electron inversion layer is already exists with the 0 gate voltage. Such a device is also considered to the depletion mode devices. So we have shown that the threshold voltage of the MOS device with a p-type substrate may be negative. This means that an electron inversion layer already exists with the 0 gate voltage applied. So such a device is also considered as the depletion mode devices. So the n-channel shown in the figure can be electron inversion layer. So in n-channel it will be the electron inversion layer. So the n-channel shown in the figure can be electron inversion layer or intentionally doped n region. So the conventional circuit symbol for the n-channel depletion MOSFET is also shown in the previous figure. So the n-channel shown in the figure can be electron inversion layer which are intentionally doped n region. So MOSFET structure, the circuit section and the cross section and circuit symbol for the p-channel enhancement mode MOSFET and p-channel depletion mode MOSFET. Figure A shows the p-channel enhancement mode MOSFET. Here this is the p-channel which is the enhancement mode. Here also this is the p-channel depletion p-channel depletion mode MOSFET. So here the circuit symbol and cross section view of the p-channel enhancement mode MOSFET and p-channel depletion mode MOSFET is shown in the figure. In the p-channel enhancement mode device, a negative gate voltage must be applied. So for enhancement mode device, p-channel enhancement mode device, we have to use the negative gate voltage. So must be applied to for creation of the inversion layer of holes that will connect the p-type source and drain regions. So if you take the p-channel enhancement mode device, here the negative gate voltage must be applied to create an inversion layer that of the holes that will connect with the p-type source and drain regions. So holes are flowing from source to the drain. So the conventional current will enter the source and leave the drain. So the holes are coming from the source. So in the case of n-channel, we are discussing that electrons are flow from source and which reaches to the drain and it leaves the source. But here the holes are coming from the source to the drain. So the conventional current will enter the source and which leaves the drain. So, a p-channel region exists in the depletion mode device even with zero gate voltage. Even though if you apply the zero gate voltage in a p-channel region which exists in the depletion mode. So, the conventional circuit symbols are already shown in the figure. So, figure 4a shows the n-channel enhancement mode MOSFET with a gate to source voltage that is less than the gate to source voltage which is less than the threshold voltage. Threshold voltage. So, figure 4a shows the n-channel enhancement mode of the MOSFET with a gate to source voltage that is less than the threshold voltage and with only a very small drain to source voltage. So, the n-channel enhancement mode of the MOSFET, figure A shows the applied gate voltage which is less than the threshold voltage. Here we are using the gate to source voltage which is always less than the threshold voltage. So here VGS is less than VT. This is the space charge region. Space charge region. So here this is the N plus region, N plus. So P is the substrate or the body. So the source and substrate is also known as the body. The terminals are held at the ground potential. So we are connected to ground. The source and substrate terminals are connected to ground potential. So with this bias configuration, there is no electron inversion layer. The drain to substrate PN junction is reverse bias and the drain current is zero. So disregarding the PN junction leakage currents. So if you connect the source and substrates, both are to the ground. So with this bias configuration, there is no electron inversion layer are created. The drain to substrate PN junction is reverse biased and the drain current is zero. Drain current is zero. In this case, the drain current will be zero. So figure 4b shows the same MOSFET with an applied gate voltage such that VGS greater than VT. So in the previous case, which is VGS is less than VT, here the gate source to voltage will be greater than the threshold voltage. So VGS is greater than VT. So here the electron inversion layer is induced in this case. Electron inversion layer is induced in this case. This is the space charge region. So this is the p-type substrate. So the same MOSFET with the applied gate voltage changes, that is V gate to source voltage will be greater than the threshold voltage. So here the inversion layer is induced. So an electron inversion layer has been created so that when a small drain voltage is applied, the electrons in the inversion layer will flow from the source to the positive drain terminal. So here the electron inversion layer has been created so that when a small drain voltage, if you apply a small drain voltage, then the electrons in the inversion layer which is coming from the source to the positive drain terminal. So the conventional current enters the drain terminal and leaves the source terminal. So in this ideal case, there is no current through the oxide to the gate terminal. Oxide to the gate terminal, there is no current observed from the oxide to gate terminal. So an electron inversion layer has been created so that when if you apply a small drain voltage, then the electrons in the inversion layer, those are flowing from the source to the positive drain terminal. So the conventional current will enter into the drain terminal which leaves the source terminal. So in this ideal case, there is no current through the oxide to the gate terminal. So for small drain source voltage values, the channel region, so current voltage relationship concepts. So for small VDS values, the channel region has the characteristics of a resistor. So we can write the drain current ID equal to GD into VDS. That is the equation 1, where GD is defined as the channel conductance which limits VDS tends to 0. So the channel conductance is given by GD equal to W by L into mu N into Qn dash. So for small values of VDS values, the channel region has the characteristics of the resistor. transistor. So we can write ID equal to GD into VDS, where GD is the channel conductance which limits VDS tends to 0. So the channel conductance is given by GD equal to W by L into mu n into modulus of Q n dash. That is equation 2. So where mu n is the mobility of the electrons in the inversion layer and Qn dash is the magnitude of the inversion layer, charge per unit area. So charge per unit area. So where mu n is the mobility of the electrons in the inversion layer and Qn dash is the magnitude of the inversion layer charge per unit area. So the inversion layer charge is the function of the gate voltage. Thus the basic MOS transistor action is the modulation of the channel conductance by the gate voltage. So the inversion layer is the function of the gate voltage. So the basic MOS transistor action is the modulation of the channel conductance by the gate voltage. So the channel conductance in turn determines the drain current. We will initially assume that the mobility is a constant. Here we are assuming that the mobility mu n is a constant value. So ID, the figure shows the ID versus VDS. So the drain current versus drain to source voltage characteristics for small values of VDS, which is shown in the figure. So on the x-axis we are taking as the VDS values, on y-axis we are taking as the ID values. So here for small voltages, here the first one is the VGS is less than VT. The gate to source voltage is less than the threshold voltage. Second one, VGS1, the gate source voltage 1 which is greater than VT. And here the third case is VGS2 is greater than VGS1. These are the, for the three conditions we are taking the graph. So the graph is looking like that. That is a straight line. So here the drain current is a function of the drain to source voltage. So where VGS is greater than VT, the drain current is 0. As VGS become larger than VT, the channel inversion charge density increases, which increases the channel current. So VGS is less than VT. So the gate source voltage is less than the threshold voltage. The drain current is 0. If VGS is greater than or larger than the VT, the channel inversion charge density increases, then which increases the channel conductance. So a larger value of GD produces a larger initial slope of the ID versus VDS characteristics as shown in the previous figure. So if you GD value is larger, it produces the larger slope of the ID versus VDS curves. So figure 6a shows the basic mass structure for the case VGS is greater than VT. So gate to source voltage is greater than the threshold voltage and the applied VDS drain to source voltage is small. So this is the basic mass structure. This is the p-type substrate. This is the oxide layer. Here the inversion layer is induced. This is the depletion layer. Here VGS1 is greater than VT. So this is the graph between ID and VDS. The cross section and ID versus VDS curves when VGS is greater than VT for a small VDS values. So it is also a straight line. We observed that. So the thickness of the inversion channel layer in the figure qualitatively indicates that the relative charge density, which is essentially constant along the entire channel length for this case. So the corresponding ID versus VDS curve is a straight line as shown in the figure. So the thickness of the inversion channel layer in the figure qualitatively indicates that the relative charge density, which is essentially constant along the entire channel length for this case. So the figure 6b shows the situation when VDS value increases. So if you increase further VDS value, the figure is looking like this. So it is decreasing of the ID values. So if a larger VDS value, so in the previous case for smaller VDS values, we observed that it is a straight line. So now we are applying the VDS values are larger one. Here the graph is looking like that. So after a straight line, it is slowly decreasing. So as the drain voltage increases, The voltage drop across the oxide layer near the drain terminal decreases, which means that induced inversion charge density near the drain also decreases. So as the drain voltage is increases, so VDS value is increases, the voltage drop across the oxide layer which is near to the drain terminal which decreases, which means that the induced inversion charge density near the drain also decreases. So the incremental conductance of the channel at the drain decreases, which then means that the slope of the ID versus VDS curve will be decreases. So in the previous case it gives the larger values of the slope. Now in this case if you increase VDS value, here the slope values are also decreases. This effect is shown in the ID versus VDS curve. The curves are looking like this. So here the slope value decreases. So when VDS increases to the point where the potential drop across the oxide at the drain terminal is equal to VT. Now VDS increases to the point where the potential drop across the oxide layer which is near at the drain terminal which is equal to T. VDS equal to VT, threshold voltage. The induced inversion charge density is 0 at the drain terminal. So if VDS increases a point where the potential drop across the oxide layer which is near to the drain terminal is equal to VT. So VDS equal to VT. In this situation, the inversion charge density will be 0 at the drain terminal. So this effect is schematically shown in this figure. This is the value of VDS. So after that it will be saturated. So if VDS equal to VT, then the line will be saturated. So the ID versus VDS curve will be saturated. So at this point, the incremental conductance at the drain is 0, which means that the slope of the ID versus VDS curve is 0. So we can write that VGS minus VDS, here VDS is saturation, that equal to VT, that equal to 1, or which is also can be written as VDS saturation equal to VGS minus VT, that is equation 2, where VDS saturation is the drain to source voltage producing the 0 inversion charge density at the terminal. So in this case VDS equal to VT, it produces the 0 slope. When VDS become larger than the VDS value, the point in the channel at which the inversion is 0 moves towards the source terminal. So VDS becomes larger than the VDS saturation value. After the saturation value, if you increase the VDS value, the point in the channel at which the inversion charge is just 0 moves towards the source terminal. In this case, electrons enter the channel at the source, travel through the channel towards the drain, and then at the point where the charge goes to 0, the electrons are injected into the space charge region where they are swept by the electric field to the drain contact. So the electrons enter the channel at the source. It will travel through the channel towards the drain. So the electrons are moving from the source which are flowing through the channel and reaches towards the drain, and at that point where the charge is 0, then the electrons are, if the charge is 0, then the electrons are injected into the space charge region or depletion region where they are swept by the electric field to the drain contact. So if you assume that the change in the channel length, here L is the channel length which is small compared to the original length L. So original length is L. If the channel length L is smaller than the original length, then the drain current will be constant for VDS is greater than VDS saturation. VDS is greater than VDS saturation. So the region of the ID versus VDS characteristics is referred to as the saturation region. And this is the saturation region. Here the VDS values are greater than VDS saturation values. Then the region of the ID versus VDS is referred to the saturation region. Figure 6D shows the region of operation. So this is the cross-section view of the VDS is greater than VDS saturation. This is the graph between the ID and VDS curve. Figure 7 shows the N-channel depletion mode. MOSFET. So here the cross section of the n-channel depletion mode MOSFET. This is the n-channel depletion mode MOSFET. This is the p-type substrate. P-type substrate or body. Which one is the source, gate and drain terminals. So in the n-channel region is actually an induced electron inversion layer which is created by the metal semiconductor work function difference and fixed charge in the oxide. So if the n-channel region is actually an induced electron inversion layer which is created by the metal semiconductor work function difference and the fixed charge in the oxide layer. So the current voltage characteristics are exactly same as we have discussed except that Vt is a negative quantity. So we may also consider the case when the n-channel region is actually n-type semiconductor region in this type of devices. So here the n-channel region is actually an n-type semiconductor region in this type of devices. So a negative gate voltage will induce the space charge region under the oxide, reducing the thickness of the n-channel region. So the reduced thickness decreases the channel conductance which reduces the drain current. We may also consider the case when the n-channel region is actually an n-type semiconductor region. A negative gate voltage will induce a space charge region under the oxide which reduces the thickness of the n-channel region. So the reduced thickness decreases the channel conductance which reduces the drain current. So a positive gate voltage will create an electron accumulation layer. If you apply the positive gate voltage, if you apply the positive gate voltage which will create an electron accumulation layer which increases the drain current. One basic requirement for this device is that the channel thickness Tc must be less than the maximum induced space charge width. Here the thickness of the channel must be less than the thickness space charge region width WD is ordered to be able to turn off the device. So a positive gate voltage will create an electron accumulation layer, so which increases the drain current. So one basic requirement for this device is the channel thickness Tc must be less than the space charge width which is able to turn off the device. So we derive the ideal current voltage relation for the n-channel MOSFET in the non-saturation region. So this is the non-saturation region. So here ID, drain current ID equal to W into mu n into CO oxide, metal oxide layer capacitance divided by 2L into 2 into VGS minus VT into VDS minus VDS square. So the family of the ID versus VDS curves for n-channel depletion mode MOSFET. Here we are taking the different values of VT. First one is the VT is less than VGS, 4 less than VGS, 3. Second one VGS is less than 0, VGS equal to 0, which is VGS is greater than 0, VGS is greater than VGS. Here VDS saturation equal to VGS minus VT. That is equation 1. ID versus VDC curves for different voltages. So which can be written as ID equal to Kn dash divided by 2 into W by L into 2 into VGS minus VT into VDS minus VDS square. That is equation 2. So from this ID equal to Kn into 2 VGS minus VT into VDS into minus VDS square. So the parameter Kn dash, where Kn dash value is mu n into COx, is called as the process conduction parameter. Here Kn dash is called as the process conduction parameter for the n-channel MOSFET, and it has the units are ampere per volt square. So where COx is the oxide layer capacitance, mu n is the mobility of the electrons. So the parameter Kn into Wn into COx divided by 2L equal to Kn dash divided by 2. So where W by L is called the conduction parameter for the n-channel MOSFET and also has the unit ampere per volt squares. When the transistor is biased in the saturation region, so if the transistor is connected in the saturation region, the ideal current voltage is given by ID equal to W into mu n into CO oxide by 2L into VGS minus VT whole square. That is equation 4. So that is the transistor is biased in the saturation region, then the ideal current of the drain current given by ID equal to W into mu n into COX divided by 2L into VGS minus VT whole square. So which can be written as ID equal to Kn dash divided by 2 into WL into VGS minus VT whole square. ID equal to Kn into VGS minus VT whole square. That is equation 6. In general, for a given technology, the process conduction parameter Kn dash is constant. So, Kn dash is the process conduction parameter. Kn dash is a constant. So, from equation 5 and 6, we see that the design of a MOSFET in terms of the current capability is determined by the width to length parameter, that is the W by L. So, from the equation 5 and 6, we see that the design of the MOSFET is in terms of the current capability, which is determined by the width to length parameters. So, the operation of the P-channel device is same as that of the N-channel device, except the charge carrier is the whole and the conventional current direction and the voltage polarities are reversed to the N-channel device. So, if you take the P-channel device, which is same as that of the N-channel device, here the charge carriers are holes. In N-channel device, the charge carriers are the electrons and the conventional current direction and voltage polarities are changed to the N-channel. So, these are the references used for the semiconductor physics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.